All right, everybody, welcome to our first lesson in Engineering Made Short. Today we're going to be covering voltage, current, and resistance. Now, we first need to motivate ourselves as to why it's important to learn this and understand it. There's three reasons, I think. The first one is it's fundamental and necessary. Voltage, current, resistance underpins every single different electronic device we use, cars, toasters, microwaves, Xboxes, etc. And it's necessary to understand it in order to apply it when you're working, in school, or in college. The second thing is that it's widely taught in your AP classes in high school, in your engineering classes in college, and even in your work site adventures when you're working in the professional atmosphere. You are going to be learning and using this all the time. Thirdly, is from my experience when I first learned this, the issue is that it's really explained mathematically, right? Voltage equals current times resistance. You can move those around and that's that. But the issue was it's not explained conceptually. So I never really understood it until learning it from myself and finally being able to understand why V equals IR. So let's get into it. So in order to make it easier to learn, our model is going to be the flowing water model. So right here I want us to picture that this circuit is a closed off pond. There's no new water entering and no new water leaving, and simply the water that we have is just propagating around the circuit from the voltage source here through the resistor there. So with that being said, it goes to our first topic of today, which is current. Current is simply, in a technical definition, the rate as to which electrons flow through a circuit. This is measured in amperes, or sometimes you call it amps. So now when we move it towards our water example, current is simply the rate as to which the water is flowing. So here, right, it's flowing left to right. And so naturally, right, a faster rate of the water moving would mean that there's a higher current. And a slower rate of the water moving means there's a lower current. And in technical terms, if we go back, this just simply means that in a given amount of time, there's less or more electrons floating from point A to point B. This is where you would maybe put your oscilloscope probe to see what the current is. The third point is actually kind of one of the most important when we apply this in the future, is that opposite streaming flow, right? So this is coming from left to right, but let's say if we have right to left streaming water, that means it's a negative current. So current flowing the opposite way is negative, and that is kind of those three main points. So again, current is the rate at which the water is flowing. So now, what if we want to limit how much the water can move from A to B? Well, that's resistance. Resistance is simply how much we want to limit the flow, and it's measured here in ohms, which is that sign that kind of looks like a weirdly shaped head. So in the water model, right here closer to us, we have faster moving water, faster current. And now you see right here we've put three kind of impediments or blocks or dams to impede the water flow, so it's hard for the water to get through. And on the farther end here, the water is moving a lot slower. So the resistance limits the amount of water that can get through, and as a result, on point 1 here, more resistance means that there's a larger difference in water speed. The water is moving really fast before it hits the dams or the blocks or the rocks, and it's moving a lot slower after the fact. Now, in electric example, it's very similar, right? You place a resistor to make it harder for the electrons to move. And this is why it leads us to kind of our transition point, this red notice. Like we have in a dam, when our resistance level is really high, right? We have this huge wall right here. The water level is much higher on one side, right? Because we have all this water right here, and it can only get through this one little path. So obviously the water on the end before the dam is going to be a lot higher and a lot more pressurized than at the end after the dam or after the resistor. So not only is there a difference in the height of the water, but all the water on the left side here really wants to get through this one little part, so there's more pressure. So like we said, resistance is how much you want to limit the flow of water, or in the electronics case, limit the flow of electrons. Now, we can put it kind of all together with the last term, which is voltage. Voltage is the difference in water levels and water pressure, and also it's called, in an electric term, and in engineering term, electric potential, right? So this is where you'll hear the differences in electric potential, but really it's not that complicated when we look at this first diagram. So this top one has a higher voltage drop. Why? It's because the water level here is a lot higher than the water level after the dam, right? Or after the resistor. So it's stopping a lot of water from moving through. Now at the bottom here, we have a lower voltage drop because the water level before the resistor or dam is only a bit higher than after it. And so, of course, like we said before, not only is the difference between these two really large in terms of the height of the water and the amount of it, but also the pressure, right? All the water wants to go through this little dam or resistor. So if you move it quickly and we switch back to an engineering sense, we can visualize it exactly the same. Similar to a water pump, the battery is pushing electrons through the circuit. So instead of this brown dam, you can think of it being a resistor, and this is preventing the electrons from moving through. So in the top example, we have a higher resistance, and the lower example, we have a lower resistance, each of which correlates to a corresponding level of voltage. And this is why a lot you'll hear in classes, voltage between 2 points or the voltage in a closed circuit is the sum of the drops. It's because you're measuring the difference in potential from point A to point B. Obviously in the top one, that difference in potential and voltage drop is a lot higher than the bottom. So simply it's a difference in water levels and the water pressure as a result of resistance. Now I'll finally put it all together, right? We know that if there is a faster current, that means that water wants to move through, electrons want to move through faster. And if there is a higher resistance, it's going to be harder for those electrons to move from point A to point B. And as a result, there's going to be a lot more water level and pressure on one end compared to the other, which is why we have V equals IR, right? The more current you have, the faster water is moving, and the more you resist that current, well, the voltage and the water level between 2 points is going to be a lot higher. And as we can see here in this little triangle, right, it's the same thing like D equals MB when you learned in your original physics classes. You can, change them around. You could do R equals V divided by I, etc. So if you know two of these, you can find the third. So that's pretty simple. That's voltage, current, and resistance in under 10 minutes, and as simply explained as I can with our example using water. Thank you, and see you all next time.